The purpose of this lab was to observe the motion of a falling object and use some of these observations to predict the motion future of the object. We did this by constructing models using Newton's second law and its derivatives. One used weight force as the only force, and the other one used drag force and weight force, but these will be discussed later in more detail. We can evaluate each computational model in comparison with each other and see which gives us the best prediction of the motion. My results were that my computational model using both drag and weight force was closer to my observations than my model using weight as the only force, as we can see here on this graph qualitatively. Let's recall that Newton's second law states that F is equal to ma. With some alterations to this formula, we get equations that predict the velocity and the position of an object. These will be important later in constructing our Python scripts for the models. To get started, I uploaded my video into Tracker. I was able to set my coordinate system with the origin being at the center of the ball before it is dropped. I set my length scale to my friend's height from his shoulder to his knees, and as well as I marked the point of mass of the ball at each time frame. It's important to see that as the time frames got later, the position of the ball was quite hard to see as it was blurry. So I had to use my best estimate, as well as the coordinate system is tilted at an angle. This is because the ball falls at an angle to my camera, as well as it is falling in the negative y direction. From the point of mass markers, we are able to get information on position and time. We are able to see the position of the object in the y direction as a function of time, shown by the blue boxes in the plot name. It is important to note that the duration of our video is 0.435 seconds. At the beginning of the video, our ball is located at the position 0, 0, 0, and it has a 0 velocity. Now, to apply Newton's second law to predict and describe our motion, we see that there is a change in velocity, which means that there is an F net. But what is F net? We don't know. So at first, we're going to assume that F net is only the weight force, which is negative mg. So now we can start our script using this first assumption. Our initialization that the ball is originally at 0, 0, 0 and it has a 0 velocity is put in, as well as the ball's mass. We have our delta t, which is the delta t of the frames in our tracker. We edit the fact that there is a weight force acting on the ball, and this is then added into Newton's second law equation for velocity, which then affects the equation for position. Our script helps produce this graph. And from this graph, we can see that our model overestimates the position of our object. So we must make a better assumption. Let's say there's a drag force acting with this force of weight. Maybe we can get a better observation and model correlation. The only change we really make to the script is that we're adding the drag force, which is proportional to the magnitude of velocity squared. To find the proportionality constant, it's just a guess and check method to find. Mine was 0.004 Newton second per meter. Our model produces this graph, and our model predicts the same final position as our observation. However, it's not perfect, as we can see here that our model underestimates the position. This can be due to many reasons. How possibly there was a distortion in the angle at which the falling object was recorded. Or we could perhaps find a different way to get the drag force. However, by looking at both models on the same graph, we see that our model using both weight and drag force was highly more sufficient than our one using weight as the only force. To the what does it mean question, which of these models gives us a better prediction of terminal velocity? Terminal velocity is when the drag force and the weight force are equal and F net is 0. So that means the slope of the velocity is going to go to 0, which this doesn't happen in the first one. But in the second one, with both drag and weight force, we see that this does begin to happen, so this would be a better predictor. Now to the what if question. That if we run this program with an initial velocity of -9, which would be happening if we zero it down, that we would get a model in which our drag force is actually going to be greater than our weight force. However, we see that, and it's decelerating when it starts. However, that we see that it is going to reach a terminal velocity. This just happens a little sooner. Thank you.